Back. So we continue the second lecture on CFD. We are five. I don't know what else, but maybe. But we have new people. Yeah, have you been there last week? You're absent, and you were okay. So, dobre. Yeah, the lecture is recorded, so you can ask me for the link. I will send it around actually, but I didn't want to make it by myself without you being asking me. So you asked me, so you will get it. Now, we come back to what I was doing last week because that was very good. I got one very nice list of questions that will help me also to do a little bit of repeat of last week. So for those who are not here, the idea is that if you want to ask question, you just write it down, okay? Now you may also ask the question during the lecture, and then at the end, just put it there. If there is nothing, no problem. I just got 5 with nothing and 1 with questions. So that will help me a little bit because today I will also cover this, what was in the questions in between of what I will be talking about. Okay, so for those of you who are first time here, we have 5 lectures. This is the second one. So we only have 3 more. And what I will want to cover during the lectures is first of all motivate you to basically do CFD. So you will see nice things. I hope that you will like it and so on. But also I will show you a little bit of the background. So we'll talk about equations as well and about techniques to solve fluid flow problems. So we are basically in the world of classical physics with no quantum, no relativistics, no chemistry. We are talking about fluids and how they behave in the rivers, and whatever, yeah, systems where the fluid flows. And last week we finished at this slide. It was about the program that I was talking about to introduce you how I became familiar with basics of CFD. And just for those of you who are not here, this is a solution of a fluid flow problem with free surface. So you have a fluid in a tank, and because of the pressure difference, you have the fluid goes upwards through this little hole that was created at time equal to 0, and therefore you have a kind of fountain. And so it looks like this. I will just play for those of you who are not here. This is a program that I created when I was a student, and I tried to participate in a student contest for the software that simulates physics. It was there organized 3 years ago. Was last contest like this. So this is an example of the solution to fluid flow problems. It's a marker and cell method, quite serious method actually. I will be talking more about it later. But let's go a little bit step back, okay, to something which is simpler. Okay, maybe not simpler, but more like that you can basically start and study it, okay? So now I tell you a story about 3 projects that I did when I was a student of master program. After this, I joined master program in computer science, not computer science, computational physics. And I went to Sweden for Erasmus program, which I recommend to everyone to go somewhere. It's very, very nice to change the environment. And during that program, we were offered courses, and I was not offered those courses that were here. It's not possible, never. So when you go to Erasmus, you have this freedom. You know, you can choose something that is not here, but fulfill SCTS points. Basically, we didn't have ECTS points here, but we had them in Sweden. And I saw this CFD course and I said, wow, I will do it because I didn't know anything about really like basics of it. I just did this one solver. And then these people told me it's impossible because it's in Swedish. So the lecture, and okay, so why don't cannot I just do what is for the course? And they said, okay, we'll give you materials. And they gave me book and told me to implement 3 things. And now I will tell you about them, because those are such that you can basically, if you want to go into this world of CFD, they are like basics and from three different perspectives. And I think it's very reasonable. Okay, I don't do this during this course because it's a little bit too short to do all those three exercises so that you basically do it. But, you know, if you want to go into this world, it's not bad to know about them and then maybe try to solve them. Because now, with me being here, talking in English, Polish, and so on, you can basically maybe do it a little bit faster. But anyway, so what is that? These are three problems to solve I was given. First is the classical simplified solution to, I mean, the solution to simplified Navier-Stokes problem. So you are given a very simple fluid flow problem. You have to simplify Navier-Stokes equation up to the point where you can basically linearize it. So you have a linear equation, the system of linear equations. You solve them and you get the solution. So it's very simple from the numerical point of view, because maybe not simple, maybe not that simple if you don't know anything about numerical methods. But if you know how to solve linear system of linear equations, then basically you can crack it easily, write your own code. And okay, so that's the first problem. The second one is about compressible flow. I will just quickly go through it because I never went into compressible flows for serious. There is actually another set of equations because we are not solving Navier-Stokes, but Euler equations, more general. And for compressible flow, this is the second problem. And the third one is the full solver for the fluid flow in driven cavity with a simple method, standard in CFD, like the Holy Grail, the very fundamental method of solution to Navier-Stokes equations. Yeah, and there is a funny story about the last one, but let's start with this. So, Couette problem, that was the first problem I was given. What is the problem? I mean, when I say problem, does not mean that it's negative. It's very positive because it's like an exercise, okay? It's the problem to solve. Couette problem is, anyone knows what Couette problem is? No, okay. It's a very basic, one of the simplest hydrodynamical system. You have a wall, okay? So imagine that this is a model of a real situation because it's like that, yeah? It's not nothing, it's not a lie, yeah? It's just a model of something which happens. You have two walls, one of them is fixed, so we always draw like that, okay? If the wall is fixed, that means you have to assume some kind of boundary condition, okay? Because we are basically solving partial differential equations. So you need to know what is on the boundaries, okay? So for this boundary, we assume the so-called no-slip condition. This will be everywhere later because it's very like standard, common, and people use it because this says that velocity, okay, I would say is equal to 0. And not the velocity as a whole, because the velocity is a vector, but the component which is parallel to the, so I will say the parallel velocity component is equal to 0. That means the fluid has a 0 velocity exactly at the wall, okay, which is basically pretty obvious. From the microscopic point of view, this is not true because, because microscopically, the wall has some kind of roughness, yeah, you can imagine. So if we go into very detailed view on the wall, this is obviously not true because the wall has some fracture, it has atoms even, yeah, which are like, there are bumps, this is never flat. But we have to assume something, and we are at the level where our wall is flat, yeah? So we are a little bit far from the microscopic view on the wall. Of course, this is possible as well. There are people studying fractured walls and fractal structures and so on. But we assume velocity equal to 0 at this particular wall. Now, the top wall is a wall which is moving with some constant velocity. So here, the velocity is equal to some kind of v0, let's say, yeah? It's like a constant velocity. So you have all these Dirichlet von Neumann boundaries. Here is the value is fixed, okay? So the velocity has some constant value. Now, what happens in the flow? Anybody knows what will be the shape of the solution now? Like, okay, we have this velocity, we have velocity equal to 0. This can be whatever. We can either put some constant velocity here, or the simplest one will be that this is periodic, okay? So let's say there is periodicity on the y wall. So we have kind of stripe, yeah? This is moving with velocity v0. This is equal velocity 0. So what would be the solution? Anyone to draw the velocity field? Okay, the top wall, of course, is moving, I mean, the parallel. So that means the top wall is moving in this direction. So it's like a tunnel in which the top wall is moving with constant velocity. So it's fixed, just like a floor. So imagine the roof is moving in one direction. Yeah, but we are in the very long tunnel so that it is like linear. And now the solution is pretty simple. It comes from the, think of what would happen. Okay, so obviously the velocity will be changing in this direction, yes? Because here everything is like the same, okay? Because the system is periodic, so the solution will be independent of x component, because you cannot distinguish from this and this point, yeah? They are the same. The solution will change along the y-axis. So this is y. So let's say this is y. So let's say this is y equal to 0. This is y equal to some a. Yeah. So from 0 to a, 0 to a. At 0, velocity is 0. At a, velocity is v. So let's say it's here is v0. Okay. This is the solution at point a. This is the solution at point 0. What is the shape of the function? Anybody? Okay. It will grow, definitely. Now the question is that, or that. No clue. Okay. Exactly, the simplest solution. And I already said that this will be the simplest case possible. This will be linear because our viscosity is linearly dependent on velocity. So we basically have the viscosity is constant, but the so-called shear rate, yeah, is constant. So we will be having the same force at each particular level. Therefore, the solution will be like this. So here is 0, so we always draw it like that. And this will be linear, okay? But, okay, now, how to solve it, yeah? So that was the question in the exercise. One can solve it analytically. It's possible. That's a case in which we can find the analytical solution. But you can also find solution from the numerical point of view, and that was the exercise, yeah, to make a full solution from two sides. Yeah, and for this, you basically find the three-diagonal system of equations, which I'm here solving with the Gauss method, Thomas and the Gauss method, the simplest possible method that can be used here for three-diagonal equations. And how to do it? Now, I will not go through this in a way that I will write on the yeah, that's the situation. I will not write equations on the blackboard. That's not the point of that. But I will show you the solution from the document that was created at this time. And I think that's enough for you to follow now, more or less, and then study by yourself, if you are interested. The only way to really like grasp something from this part is to basically sit down and try to repeat it and do it after me, okay? Or after books that I was using, because obviously I was a student using the books and finding solutions here and there. and I found them. Okay, now to recall the question from the paper that I got last week, as I told you, I will be doing that. I will now just repeat what are the symbols in Navier-Stokes equations. Let me find the pointer. Yeah, it's here. Okay, because I was asked to do it again. So the Navier-Stokes equations for incompressible fluid in a full set is here. This is the, let's say, it's not most general way you can write Navier-Stokes equations, but it's the most general at this course. So it's the most general for incompressible fluids for the situations that we will be working with. And now we'll go to simplify it. And I think that will be now very pictorial for you what we really simplify in this particular system, so you will understand more about what this equation means. But let me recall again the symbols. So U in this equation is the velocity field. It's not a velocity in one particular point. It's a vector field that is dependent on time. So basically, U in my equations is the function of x and time. Of course, it's a vector. So if you look at it, as I like to look at it, of course, in the discretized world, because I'm computational physicist, so I always discretize in my mind. So I see vectors everywhere, yeah? So the one letter U is the whole vector field everywhere. Okay, it's of course continuous in the equation, so it's like more even very, very dense, yeah? So you have a vector everywhere. And now you can do many things with these vector fields thanks to numerical, not numerical, uh, uh, thanks to those operators, yeah? So partial operators. So basically you can take nabla, yeah? Sorry? Yeah, you can transform them using operators. And those operators are working on the vector fields, yeah? So basically, and now, okay, we can go into very detailed description what each of those operators mean, and we will do it later. But now what I want you to know and understand is what is the physical meaning of each of these terms, because we will simplify, then we will see on simplified equation what are those operators doing. And now what is this equation really? It's kind of like second Newton law, because on the left hand side you have acceleration. It's a partial differential operator which takes the derivative of velocity field. So it's like taking derivative in each of these points in the space. Okay, now on the right hand side all those terms are forces, so now divided by mass, of course. So it's like those that are acting on each individual element of the flow. And let's start with this. This is a gradient of a scalar field phi, which is the pressure divided by the density. Okay, so this is a gradient of density. It's like if you have a potential, so density, I mean pressure is kind of potential field, yeah. So if you have a potential in electromagnetism and you take the gradient, what does it mean? You get a force. It's exactly the same. You get a force because of the pressure difference. The force comes not from the pressure. It comes from the pressure difference. It's like that. So now this gives you the force from the pressure. So it's like a pressure component. This component is a component related to viscosity. And it's exactly the mechanism, physical mechanism that gives you this shape, because so the viscosity coefficient here is multiplied by Laplacian of velocity field. And okay, this term is called viscous term. Now, this term is due to the dynamics in the flow. If you have elements of fluids that are moving around and you look at them, like let's say you have a droplet of fluid, okay, there are some particles. Let me try to put some pictorial description to it. And this group of particles is moving it is advecting the momentum with itself. So the momentum is advected. So, so this term that is here is called advection. It's like a transport of mass that is transporting the momentum as well. So imagine that the fluid is not only moving a mass, it is also carrying the momentum information with itself. Um, all this together makes it very, very hard to solve. Therefore, we have to use some special algorithms, and there is no one that is always working and is like state of the art. So it's actually very complex, because if you combine all those together, you get and for instance, the viscosity is very high, then the combination of all those terms makes the equation very, how to say, it's not a complication. It's more about the solutions are complicated, are very complex. Everything can mix. Basically, you know what water is doing. Yeah, it is mixing and everything. And this equation is really describing everything. It describes turbulence, but we cannot solve it. We don't know how to solve it. Therefore, we don't know if the solution exists. There's this millennium problem. Yeah. To solve Navier-Stokes in full set for the high Reynolds number in turbulence regime. But people are solving this little equation and get turbulent effects in so-called direct numerical simulation. That means if you make the computational mesh very dense and you solve this equation from the like in full set, with proper numerical methods, then you can obtain turbulent effects. The problem is that you can get it in very small scale, in a very short times. And it's very, very hard because this grows exponentially in time. Okay, okay, and the second equation here is continuity equation. Here written in which we don't have derivative of density, because we assume that fluid has a constant density. It's incompressible. For incompressible fluid, we just have this divergence of velocity field. Divergence has to be zero. That means there is no source or sink of water. And if the water was compressible, so for instance, you can imagine that you have a density field that changes in time. So let's say there is a high density and low density fluid. Yeah. If I take part of this system, I can expect that some of this high density part will go out. Yeah. Because there will be some fluctuations, but not here. Here, das has to be zero. Then that means we assume that nothing go out and nothing goes in. Everything flows through elements of the system. Yeah, that means it's an incompressible flow. Okay, which for instance means that these two equations cannot solve the so-called shock wave. Yeah, if you have aircraft that goes with a very, very fast, close to the with the velocity close to the velocity of sound, then the shock wave is created, and these two equations cannot capture this. Now I will show you this second report in which I have equations which capture, but I must say that second one was blindly made by myself from the book. But anyway, so the solution looks like this. Now, I will show you the equations in a moment. How did I get the solution? We will go together through it, so you may have some questions and so on. I also have a nice source for it. But let's say first see what is the solution. So we have analytical solution, which is linear. This is basically the function there. I will show you how to obtain linear solution. And then here we have a solution that goes in time, because the way that I was solving the equations was iterative. So the numerical method was giving me the time solutions, and basically it was not that I solved exactly this at one step. I had to iterate it, and then at the end I got Actually, I showed, you see, I showed the analytical solution here. I was clever as a student. I showed this analytical solution, but my last numerical one was this. But clearly you can see it converges to this one, yeah? But I don't know why I didn't show the last one. I don't know, maybe I didn't get it. Who knows? If someone wants to repeat, there is a code in the report even. I know that it's, from the didactical point of view, it's not nice because uh, you will not be really, where is the report? It's here. You will not be very motivated to do it if the solution is there, but I recommend everyone that wants to go into this world to once solve a problem which is that simple, because this gives you a lot of info. So that was on Linköping University. Okay, I was actually given the task and no support. They didn't give me even some lectures because they had all the documents and everything in Swedish, but gave me good books. Okay, so let's go through this so that you see the way I was thinking and the way the solution was made. So we start with the incompressible Navier-Stokes. You already know, yeah? It's a kind of standard now. You will be given this again and again, and continuity equation. Now for the Couette problem, we will formulate it in a way that the equation is simplified, because we don't need all the terms that we have in the Navier-Stokes. And now we will do it in a way that we think is from the physical knowledge about the system. First of all, okay, first of all, we know that there is no pressure gradient. One can say, where do we know there is no pressure gradient? So if you open the CFD book, which is introducing this is written, so in the system, there is no pressure gradient, black. That's the explanation. So let's think all together, yeah? If we have an incompressible fluid that fills the system like that, where is the source of pressure that can be in any hydrodynamical system? First of all, and this is from the school, I'm sorry for saying that, I don't like it during the lecture. It's not like I ask you, but just think. We were given two sources of pressure in a primary school, high school, or whatever. First of all, what is the force that is making the pressure in, I don't know, in my coffee, for instance? Gravity, the static pressure, yeah, the static force. And here we assume there is no gravity. So first of all, we remove gravity term, yeah. In the equation that we had before, there was a G written, yeah, you remember? So that was this. This term is removed at the very beginning. If G is removed, then we need to think whether this term is existing or not. G is already not there, yeah? So we want to get rid of pressure. One source is the gravity. The second source would be what? Yes and no. The density gradients would create some kind of pressure differences, but there is no density fluctuations. We assumed that at the beginning. The other one would be some kind of obstacle in the flow. If the fluid flows towards some obstacle, it is acting as a force. It's acting with a pressure. This comes from the Bernoulli laws and so on. You can basically think of it as a dynamical pressure. Here, there is no possibility because there is no obstacle. There is no normal force of the flow. Everything flows in this direction. This is from the very often in physics, we are simplifying equations, and this exactly happens there because of the symmetry of the system. The symmetry is like this. We have only a force which acts in this direction. We know that the momentum, okay, there will be momentum transfer in the y direction, but there is no difference here. So there is no possibility that there will be some kind of a pressure in the x direction because we don't have obstacles. Nothing flows towards something. There is only a so-called wall shear stress. And this comes again to the questions I had, because I mentioned this in the previous lecture. WSS is a term that is very often used in biophysics. It's a wall shear stress. It's a force that is acting on the wall, okay? with a fluid moving along the wall. So it's a force which acts in this direction, in parallel direction to the wall. It's wall shear stress. Okay, it's a kind of technical term because it's basically the it's an force that is due to the viscosity effects that happens in the flow, which are described by this equation, but they happen at the wall. Okay, so it's a wall shear stress and it acts in this direction, but there is no normal force. Yeah, there is nothing that would go normally to the surface, and the pressure is what? It's a collision of particles normal to the wall, which obviously happen here, but we are not considering them as a pressure that changes anything because there is transport of flow only in this direction. Okay, maybe hard to like give 100% explanation, but now I hope you have this intuition why the pressure is removed. Okay, so then we get rid of this term. Okay, pressure term. All this is assumptions, yeah? We are looking for the solution. Now we are doing some kind of, not cheating, but simplifications, and we will see the solution if it's true or not. That's also a kind of a way to go here. Now, we will also ignore convection effects. Now, this is an assumption in the our derivation. We basically get rid of this. Why? Because that's actually something which we don't like, but we very often do. We know the solution. We know there will be no vortices. We know there will be no dynamics in the flow. We know the solution will be very simple. We actually assume what the solution will be. And from that, we can basically get rid of this term, because this term is responsible for all the dynamical situations in the flow. Okay? And then we write our equation in this form, which is now containing of two parts: the change of the solution in time, which is here, and the Laplacian term. This is the viscous term of our Navier-Stokes. So it's a viscosity multiplied by Laplacian of velocity. Those of you that know the diffusion and those processes, they're already a little bit familiar with this equation, because it's just a Laplacian of vector field multiplied by a constant. And that means we are very close to the solution, yeah, because we can okay, but let's first utilize our second equation, which is the coming back here, equation 3 is a continuity equation in which the density is not visible, but we have the divergence of velocity field. And this divergence can be written in partial differential form. So we write it down as, where is it? Here. Okay, 7. Okay, this as derivative of velocity field along x and the derivative of the y component along y. Let me write it down here because it's not that obvious maybe. Our velocity field here, we assume it's two-dimensional. It consists of two components, u and v. U is the x component, v is the y component. Now, if we have the divergence of this, it's basically can be written, yeah, as du over dx. Am I right? Yeah, plus dv over dy. So it's basically the divergence of this velocity field is this because this is a vector multiple. So let's not go into details of math here, but it's basically that. Yeah. So now if we have this and we know that this is equal to 0, yeah, because this is our assumption, we know that there is no u velocity. Yeah, because sorry, there is no v velocity. It's my mistake in my report. That should be v. There is no v velocity. There is no y component. Everything flows in x direction. So we have only this term. So then we can make it, and then du over dx is equal to 0. Okay, that means the the derivative of x should be 0. Okay, and okay, now we do some. Okay, we assume the v is equal to 0 at okay, now the equation 6. Okay, let's go now into the boundary conditions. And now this equation 6, which is there, it's too large. That's true. Now I know why people prepare notes for the lectures. Yeah. No, I'm kidding. So equation 6, we want to write in such a way that this operator is also written as a partial differential equations. And this is basically the second derivative of x component over over y. Yeah, so d squared u d y squared. Why there is no d squared v? Because v is equal to 0. We already know. Then, and this is because of our the previous assumption. Now we have this equation, and this is now actually the simplest possible for this particular problem. So we have the derivative of u component, and we have this viscous term, and now we want to solve it. And that's actually the problem itself to solve. And there are some methods for that, different ones. And in my report, so we basically simplified Navier-Stokes toward this. And believe me or not, but this is Navier-Stokes equation for this problem. Yeah? So now you know the way I tried to simplify it. Yeah. Okay. And first of all, we can analytically solve it. I was so long time ago, I was solving anything analytically, but let's go through what I had here. So we basically get we want to find an analytical solution for velocity profile of steady flow. Steady in CFD, in this fluid mechanics, means there is no time changes in the flow. This is also something we can assume about this system. If this top wall is moving in time, then the final solution, final one, will be steady, means there is no time derivative, because there is nothing to be changed. Because if this is constant, then the equilibrium solution to this problem is such that this will be no longer changing. Because of there will be a momentum, there will be, let's say, friction on the bottom wall, and there will be constant velocity here. So there is no momentum put into the system. Therefore, again, our equation simplifies. Okay, so I was actually not lying, but I was not completely completely right that this is the final Navier-Stokes. The final one will be this, because we even simplify by doing the solution simpler. Now we can simplify further, because the viscosity term can be now just basically thrown out because it's constant. And now we see that our second derivative is equal to 0. So basically our equation can be written in this form. Now we can assume some solution, and it's pretty simple because this basically works. So this is the solution. We put some boundary conditions. Yeah, so we have the velocity at velocity at a boundary, which is here is d, not a, but at this boundary the velocity is constant, at this boundary is 0, and we have the linear solution. So basically the solution is here. Now how about the numerical solution? Okay, well, now we go into the CFD world. Now numerically, how to solve the same equations. So first of all, we define non-dimensional variables. So we put the velocity with prime, which is the velocity in a system divided by the velocity at the top wall. Okay, so this is our like nomenclature. Now everything that will be in the system will be from 0 to 1. So there will be so people working with numerics, they like it. They put very often those non-dimensional variables, and we are happy because then everything is simple to. We don't have to put how do you call this in Ah, mm, how do you call it in English? No, talking in English is very nice at 8 o'clock in the morning. Okay, we basically it's dimensions. We don't have dimension, no physical dimension. Yeah. Anyway, so we have these variables now. With these variables, we will write our equations again, and basically, yeah. So we put them into the equation in which you have this time derivative, you have the second derivative, the viscosity, and so on. You can very easily follow it. I will not do it on the whiteboard because everyone can do it by himself, and these days Mathematica can do it probably. Okay, so we have these non-dimensional equations. We go into, now we remove those chars, and this is what people very often do, and this can be confusing when you read books, because we basically get the same equation with some variables here, and this looks the same as it was before, but it's different because we skipped this. Yeah, so keep in mind when you read CFD books, because everyone does it. In computational physics, this is very often that people does it. And then you have those terms that are just basically the non-dimensional numbers. And now here, one can define at this point, in this simple equation, those parameters that comes from non-dimensionalizing equation. Okay, we had this simple equation. Remember, we had this simple equation here, which was time derivative of u equal to viscosity times the second derivative of u over y squared. We non-dimensionalize it. Okay, that's more important to me, so that you understand the procedure than we doing that here. Yeah, you can do it by yourself. That's simple. If I did it being a student, you can do. But if you do it, you can find that in this equation, these parameters appear. The velocity, the d, which is the size of this, the density, and the velocity of this top wall. And if you get this out and you name it Re, then you get the Reynolds number, which is one of the most fundamental thing in CFD, because it's very useful to think in terms of Reynolds. What is Reynolds number? Reynolds number is non-dimensional from the procedure we did here. So now you see how to derive Reynolds number in simple case. It's a non-dimensional number that relates the viscous to momentum forces. So you have momenta in the here, and the viscous forces here, the viscosity term. Is non-dimensional, and it tells you what is the relation between momentum and the viscosity forces. So that means, now, what does it mean? That means depends on the Reynolds number. It's non-dimensional, so it's a number. It can be 0.1, it can be 1, it can be 10, it can be 100. Depends on the value of Reynolds, the type of this flow is changing. So the Reynolds number tells you what is the component of momentum in the flow, or what is the component of viscosity in the flow, like more or less. Okay, it's like a number that defines the type of the fluid. Here, okay, here. Yeah, so basically the Reynolds number is dependent on many factors. For instance, the viscosity is here in the denominator. What does it mean? That means that if viscosity goes down, so that means you know what viscosity of fluid means. So just physically, if the fluid has a high viscosity, okay, it's like highly viscous, it's like oil or honey, yeah, or whatever which flows very slowly, it's viscous, yeah, you know that. On the other hand, if something has a low low viscosity, it can be like a water, like air in the, so it has a very low viscous component, but it has a much more, this momentum component is much larger in the low viscosity fluids. Then that means, so again, high viscous fluids means the honey, the oil. Highly viscous means low Reynolds. Low Reynolds are much simpler to solve numerically, much simpler to solve analytically. But high Reynolds number flows are very hard. These are flows where the turbulent effects appear. And the turbulent effects appear because this nominator takes over, and it's like taking the whole dynamical part is dependent on the momentum of fluid or the advective term. Everything flows everywhere, and it's very, very hard. So here, in this particular example, our system is actually Reynolds independent, because if we take the derivative equal to 0, we can basically multiply by Reynolds and get rid of this problem. That's actually because of our simplification, it goes like this. But anyway, now you see the way you can find the Reynolds number in such a system. Okay, what the Reynolds number is dependent on? It's dependent on viscosity of the fluid that fills the system, but also on the size of the system. Okay, because if the system is larger, then the viscosity effect is much lower compared to momentum, which is carried out by the fluid. And if the velocities are higher, so that means here the velocity of this top wall, then also the momentum takes over. So the higher velocity means higher Reynolds number, yeah? Larger systems means higher Reynolds number, and so on. And now, why this is so important? This is important because if we didn't have Reynolds number, we would not be able to do experiments in many situations. What people do, they can, because the physics is the same, independent of scale. I mean, of course, in some range of scales. But what people do, imagine that you have a car. Okay, now I will draw the BMW. Okay, and this is a real car. Now, if you want to do the experiment in a wind tunnel, so basically put an air and compute drag in order to optimize it and make Tesla track, yeah, to make it less drag, yeah, for the so people do this. They build huge wind tunnels. Now, actually, the news from yesterday was that Poland will be the first world in Poland, the first wind tunnel for the ski jumpers will be made. And I don't know what will be the construction, but they advertise that we will be the first one in the world. And I don't know if they are not planning to make an air tunnel in which the ski jumper can really like perform the jump. That would be really fantastic. I don't know what they plan. I have no idea. I didn't read about tech, but they advertised yesterday that the decision is there. So maybe this will be full one-to-one wind tunnel for ski jumpers in a way that they can actually really be there. Yeah, that will be fantastic. But anyway, so that is very hard. What people do very often, they scale the problem, because what matters is the Reynolds number. And as you know, Reynolds number is proportional to the size of the system. Now, if you scale down the, let's say, this car 10 times, so let's say it will be 10 times less, smaller, then you can use the model which is 10 times smaller. So let's say it's here, the smaller one, okay? Which is basically like this size. Put it into the wind tunnel that is of this size as well, also scaled, and just put a viscosity of the fluid which is higher 10 times. So 10 times higher viscosity in smaller system is the same as the original viscosity in large one. Then you can perform experiment here and do the same optimization. So basically, Reynolds number is a key word in this course, because it's in CFD. Like everyone knows, everyone is like the. If I had to do an exam here, I would ask, what is the Reynolds number definition? Yeah, because that's pretty much the thing. Okay. But regarding the exam, because I was told that we are actually going to have an exam, but I don't know if we give a grade for the course labs and for the exam. If we give only for the labs, then you just do the those two exercises. If for the exam, there will be like a little thing to do afterwards so that you can fulfill the exam, but it will be practical. I'm not going to do a proper exam like asking you questions about Reynolds number, because what I care more is that you can do something simple, not that you spend 3 weeks, but who knows how much you spend. Anyway, something simple will be to be done. Okay, anyway, so this is basically Reynolds number definition, which you already know. You know how did I go into this, and then the numerics. You see, there are many things: math, physics, numerics. There a lot of stuff in CFD world. It cannot be different. It's like this. It's pretty complex from many perspectives. But anyway, so this equation can be solved analytically, which we know. It can be simplified because we can basically get rid of this term and then solve this as well numerically. But then you get into the system of linear equation of different kind. But I used another approach, which was suggested by people from this course, was to keep the time derivative, okay, and find solution in time, which can be done with so-called Crank-Nicholson technique. So we basically take the discrete representation of this equation. So what is the discrete representation? You take each of the partial operators here and basically discretize it with a proper accuracy, because those discretizations can be different. Yeah, what I used here is a so-called finite difference discretization. So I basically discretize on a grid of regularly spaced distances. So our system is discretized from 0 to some n, and we basically go discretized our function on this grid. The same discretization is in time, so we basically have a constant time time factor delta t, and there are books for numerical methods in which you have this discretized operators. So basically this one is not my invention. It's basically an operator which has probably second order accuracy in space, and I basically take I basically discretize this operator, the second derivative here on the grid. And we have the Reynolds number, delta t, and here is the time discretization. Now, what we will do here is to group the terms from the time, which is the following our steps on the one side and one on the right side. Those of you who want to do it by themselves have to first of all look into Crank-Nicholson technique. It's it's not only for CFD and for Navier-Stokes, but okay. If we group those terms, sorry. Okay. And we basically write down those symbols that on the left-hand side we have the some kind of coefficients that are before the u on the next time step in the, basically what we do, we want to solve it like this. If we want to, this is the uj minus 1, this is uj, and this is uj plus 1. Yeah, this is j plus 1, j minus 1, this is j. We group them, and on the right-hand side will be those terms that are from the previous time step, and we have those constants. Then we basically build the system of linear equations, where on the left-hand side our system contains of the velocity on the next time step, and on the right-hand side there is velocity in the previous time step. This comes from this here, yeah. This is this equation. Okay. So sorry. So we have the velocities on the next time step. These are on the right-hand side, and on the left-hand side we have velocities on the previous time step. And yeah, and this gives us the coefficient matrix A, okay, which is basically built of those BA values, okay. So we have the problem of solution of the whole system is basic of the whole system in time is basically the three diagonal system of equation, the system of equations with three diagonal matrix of coefficients, and this can be solved with numerical method, Thomas method. And now, if you want to really understand this, now I know that you probably see like, okay, now it's very fast. There are some coefficients, this, that, I don't know. You have to basically follow it. It's no possibility that you don't do it by yourself. And I will not give it on this course because I think we can do something more interesting at some point. But this is basically, so this is the Thomas method of solution to three diagonal system of three diagonal equations. Okay, so you have a linear system, and you basically go and step by steps. The solution is pretty simple. You basically go and just subtract the next from the previous one. This is a Thomas method. Okay, the whole algorithm is basically in books, and then you get this solution, which is in time. So basically, that's the numerical solution for this. Okay, and now let's see okay, I was studying some numerical stuff here, and you also have the whole implementation, which was from scratch. I was doing like a matrix here and so on, and I used Gauss elimination because the Thomas method is really Gauss elimination problem, and so on. And the creation of matrices is here. Yeah, I just may go from the yeah, step by step, create from the equations all the coefficients and create a matrix which is three diagonal. Okay, that's it. It's nothing more. What is appendix B? Because I was using this for another problems as well. Okay, and there are three references that I recommend. The book, Computational Fluid Dynamics by John Anderson, it contains of the whole solution that I gave you here in this report. It's not that detailed, so I had to find this and that, okay? But if you are interested, then this book is in our library because I bought it some years ago, so it should be there. Might be on my bookshelf, but I don't know. I think I gave it back. And if not, then it's in my office. I can give anyone. Okay, so that's the Couette problem. And let's leave it because, again, and I really tell you that honestly, if I went through all this here, it's not possible to really grasp it if you don't do it by yourself step by step. Okay, so just think, if you want, just we can discuss more, then come to me. It's a specialized lecture, you can do it. Okay, then if you solve it, you have a numerical solution to this simple equation that can be solved analytically. Okay, so that's the Couette problem. Any questions at this point? Sorry? Mm-hmm. Okay. Yeah, okay, there are two ways of solving the equation that we have here. So the equation is here. Okay, it can be written in this form with Reynolds number. It doesn't not matter because the previous one was the same. And one solution is here. This is analytical solution. Okay, I use the boundary for analytical solution. Okay, and the analytical solution is basically u equal to ue over d times y. So basically, this is analytical solution. It finishes here. I don't do anything more about it. It's like solved. We can live it. We don't have to solve it numerically. The task in this particular exercise was, okay, you have this analytical solution, now do it numerically. And for numerical solution, you have to follow my steps and then build these matrices based on this um, um, discretized version of the partial differential equation. This is discretized on a grid, okay? So you take this equation, you discretize it, you have re, which is there, you have this, which is there, yeah? So you have this discretized version, and you use Crank-Nicholson technique for that. Then this, I cannot introduce this here because I would need to give you numerical methods step by step, but the Crank-Nicholson gives you all this time derivatives and so on. This gives you, this is from Crank-Nicholson. Now this can be reformulated, this equation, on the whole grid in time in the system of linear equations like this. If you build it, then you get the matrices. And the matrices are with the A and B. Basically, A and B are there, and you build up the system of linear equations, which now might not be that simple for you to understand, but if you get the document, read, and try to follow it, okay, it took me 4 weeks to make it when I was a student, yeah? And it's not my point to do it now here. It's like more to give you the example and give you some kind of motivation maybe to jump in, and then if there will be one person who goes and follow it during this course, that's okay for me. That's okay for CFD. You can do it. That's a very nice task, but it's all about what interests you, okay? It's a very basic and fundamental from the bottom approach. Now, okay, any more questions? Don't hesitate to ask or write it down, yes? Okay. Yes, but from the symmetry of the system, there is no there is no mass transfer in the y direction, and then the pressure here will not accelerate the flow. So from the symmetry, the flow will be only in x direction, and there is no gradient of the velocity in x direction. Yes. Yes, yes, because from our the construction of this problem is such that the flow will be only in this direction, because there is no possibility that something will flow in the y direction if this is incompressible, bounded by the walls. Okay, it's kind of assumption. I agree, because it can be solved with the pressure as well. I agree, but there will be no influence on the flow from this term. That's the assumption, and then we remove it from the equation. But you are right. From Bernoulli, the velocity squared would give the pressure values here. Yeah, because the pressure will be there, but no the gradient that would act as a force that changes the momentum from the symmetry. The differences between velocities in y component will not act as a source of the momentum for the flow. So it's kind of assumption that there is no vortices in the flow. But, okay, let's go, because that's a very good question. If you increase the Reynolds number heavily, like to 10,000, okay? This will be so fast that it will go like with the velocity 1,000 times faster. What happens in Couette flow? You will see turbulences. So you will see pressure differences. You will see vortices in the flow. That's true. But here, to solve it, we need to assume it. And this gives us also a solution. And if you make a physical experiment in a tunnel, and the Reynolds number will be enough low, and then this pressure term will not take any part, and the solution will be like this. So this is not hypothetical situation. This is something that happens. Yeah, in very many situations, the linear flow is visible. Okay, good. And okay, so that's the Couette problem. Any more? I mean, this is a fantastic question, because that's actually very open. It's not that we are sure that in a system like this, pressure does not exist. It's like, I would say more precisely, our assumption. Okay. Any more? I can do it for you, no problem. Just about stuff like this, ask me always because I always forget and I have like, so just send me an email and I will. Uh, before the lecture. No, yeah. Yeah, sure, I will do. And the recording is there, and this one is hopefully recording. Yeah. If I don't forget, then if you like, I can put on Teams, but there is not everyone is there. Are you there already? Yeah. Okay, good. Okay, so yeah, pretty heavy stuff. It's like not very easy from numerical point of view, I must say, because you need to build those systems of equations and so on. But it's possible. For me, it worked, but practically, it's not that. Um, Okay, any more questions? If not, write down. You can make more to me. Okay, now we are like what? Wow, it's impossible. It's already 15 minutes before the end. Really? No, am I right? Yeah, 8:15. So that means we finished 9:45. Oh, phew, for Couette problem. I'm better and better on lecturing. Now I can do like 30 hours lecture on CFD probably with the same material. And so talkative. No, I wanted to say more about actually these three things because I think that this can motivate you and those reports are available. And I'm very open to work with one of you on them. But it's like a process. It's not easy. It's not like you get it just done, but you can follow it. Now the more heavy stuff with the physical part because I'm not that much into the compressible flows, but the situation is like that. You have so this is the second problem I was given. You have a problem of a flow over a flat um, wing or whatever, and this wing is uh, turning on with some angle, okay? And now the idea is that this is supersonic flow. So it's a flow which goes beyond the speed of sound and turns around the convex, so around this corner. We have no viscosity. So from physical perspective, that means we don't have Navier-Stokes, we have Euler equations. And again, it comes down to the solution of three-diagonal system, but the solution is completely different because to solve the Euler equations. Now I tell you what I remember. One wants to study compressible flow, no problem. I didn't want, but I did this exercise. And the solution was like that. It's a marching solution. You have some solution on the boundaries here, and you march down through the numerical mesh and solve it like a vertical line by vertical line. So you do solution step by step. It's called, there is some name for that. It's in my report. Let's open it. Um, so this was actually the one that I knew the less, but it was the simplest to do for me from those three. Because for the first one, I spent a lot of time. For this one, the solution was in the book. So I basically rewritten it step by step, but it was pretty hard from technically. Okay, so you have all these parameters, you have angles in physics space, you have the Mach numbers, in the flow. So there is like, and the solution, oh, okay, McCormack predictor corrector, okay? McCormack, numerically, this is McCormack method. So it's like, again, marching through the system, step by step. Okay, the equations I solve are here. Where is this? These are the Euler equations written in this simplified form. They are written like this because then we basically go through the solution for f and g in parallel. It's like a bundle of physical parameters that we solve for. It's pretty complicated equation. Basically, all this goes here. Of course, all this goes there. And then if you do it, then you have Euler equations. I don't go into physics there. There are also some assumptions. there is no body force, there is a perfect gas assumption that you have to assume something about the state equation because it's compressible. So you need to know what is the pressure density relation and so on. You need to assume something about temperature and so on. But I was more interested in numerical solution because it's interesting from the numerical point of view that you are working on a grid which is changing with the position. So the grid is expanding. So we basically know something about the solution as well. I mean, maybe not about solution, about the system. And there is a function that tells you what is the size of this mesh, So you transform the grid. So it was my first ever experience with the non-regular grids. And yeah, I discretize Euler equations with this McCormack scheme. It is described there. Let's not go into algorithm much. It's basically a bunch of again, the operators are discretized in space, and we have the predictor and corrector step. What predictor corrector means in numerics? You basically solve the equation, but you do errors. So you use some kind of proxy or a kind of additional equation that tells you what is the size of the error you do. That can be different from different perspectives in different problems. But you basically make the predictor, and then you say, oh, my solution is not right. Let's make a step back and do it, for instance, twice in time, with a smaller time derivative or something like this. This is predictor corrector step. And you can find it in many different situations. Here is quite complex. Actually, this is one of the most complex stuff that I was doing in CFD. And yeah, and it was pretty hard to get results, but yeah, step by step, I just did it. Let's see what is there. There are some. Yeah, I basically got the velocity distribution over this step, and this was then compared to some solutions from the book, and they were right. Basically, what is there is the velocity change from Mach 1 to Mach 2, which was basically kind of a shock wave on the corner, yeah, and yeah. Uh, yeah, I think so. That's basically the yeah, the white area is because it's here. Yeah, the velocity is much higher here, so it's a kind of situation like this. There is also temperature field. I did some temperature transport and so on. I think so. No, it's a scalar field T. In even in with the I don't know why there is some. Let's leave it for the reading. No, I recommend the book. Okay, the book of Anderson is giving a whole chapter on the problem like this. The solution here I show you because it's a kind of example of stuff that you will not see here at this institute. Nobody works with compressible fluid like this. So it's good to know that anything like this is possible, but let's leave it. I'm not specialist on compressible flows. It's like that's enough for my explanations, okay? So 5 minutes is enough for compressible. And now let's go into the best one, because this is something that gives me actually gave me the much of my, where is it? This was my first step to the real CFD world, and I actually like it much, and this is driven cavity problem. Actually, that was the reason I decided to do the course, because when I saw the problem list, I know Couette problem, what is that? Oh, okay. Prandtl Meyer, I didn't know anything what is this, and I was not interested in aircraft transport and so on, and in high-speed flows and shock waves and so on, but driven cavity. When I saw that this is possible to do in this course, it was motivating me much. What is the problem here? It's the most standard, typical problem in CFD. It's a driven cavity. It's a physical phenomena that happens in a system in which the fluid is closed in a tank. So we have no slip boundary conditions. You already know no slip was there. So you have no slip boundary conditions on all the walls except the moving top lid. And this lid is moving with some velocity, let's say u equal to u0. And what happens in the system like this? So it's closed. You can see it when you have a balcony, okay? And there is a wind, and on the balcony there are leaves. If the leaves are on the balcony, sometimes what happens is that if the leaf is there, liście, yes, they can start rotating, turning around in the when the wind blows over. And this happens because the vortex is created inside of this balcony, and this is exactly what we will be studying here. It's a driven cavity. Now, the driven cavity problem, again, is a standard because it is used to benchmark numerical CFD codes very often. So many papers in my community are where people are working with different numerical methods are using this problem to verify if the solution is right. Which is, of course, not the ultimate proof that something works fine, but yeah, people are using it. So, okay, so what happens if there is a top lid is moving, of course, in this direction, so it's like a moving linear lid. The system is two-dimensional. There is a momentum transfer. The momentum transfers from top lid to the fluid. So that means the particles that are close to the lid will be dragged with the lid. And this momentum will, of course, transfer into the system. The way it is transferred is itself nice phenomena, especially at the corners. Numerically, corners are terrible to solve, and this is always a problem. What is the solution exactly at the corner where the no slip condition meets with the top velocity? So it's like miracle that it works. But anyway, there is some transport of the momentum into the system. Then what does it mean? The particles have to turn the fluid, because the fluid is incompressible, then this momentum will create a vortex. And even for a very low Reynolds number, the vortex will appear. But if we increase Reynolds number, okay, Reynolds is a key here, because if we increase Reynolds, the way this vortex looks like, the number of vortices in the flow, the type of the flow changes. So it's an interesting physical phenomena because you can observe that apart from the main vortex here, some kind of secondary vortices may appear in the corners. So with the Reynolds, there can be even the third degree corners, fourth, and so on. There is a cascade of corners. And there are, so in this particular result, for instance, so it's actually my result from the report. And the most interesting is the visualization, because I was playing a lot to show it in a way that I see the physics there. And you have these puffs of particles that are flowing in the water. What you see are several phenomena. First of all, you have this secondary vortex. Second, you have a vortex in this corner as well. It's not that easily visible with this visualization. It's actually very hard to visualize it because the velocity here is order of magnitude larger than velocity in this corner. And then if you looked deeply here, there will be another one in the corner because the physics is like this. In the corner, there is a kind of singularity, I would say. There is a kind of always will be this fluid will want to accelerate another one which goes in this direction. The deeper you go, the more complex it is. You have to obviously finish at some resolution. You cannot go deeper with the numerics. But if you had a very fine numerical mesh, you probably would end up with a very interesting stuff happening in the corners. And this is what people study. It's like thousands of works about driven cavities because they are interesting. They are not solvable analytically. There is no solution that you can do by hand. And you can see this turn back here is interesting. This is not a numerical kink. This is a solution that goes this, and this direction. And there are vortices that appear in this area. And yeah, people from fluid mechanics can talk hours about vortices, which are here and there. And this is actually very, like, the main goal of this project was to actually get a vortex in driven cavity. Okay, this is a solution after, many hours. And then that was the biggest problem I had was to solve it. And now how I was approaching that. So the idea was we have, again, incompressible Navier-Stokes, you already know. Fluid is closed in cavity, so the system is similar like here. But you cannot assume those assumptions that we had before, because, for instance, the pressure here will act everywhere. The pressure will be a key gradient. Also, there will be a convective term, because all this stuff here, the momentum transfer, the mass transport, and so on, this all comes into this convective term that is. So we have to basically find a solution to full Navier-Stokes. Gravity is removed because gravity does not act here, and we have a top-driven flow. There is no solution. We have methods which are called the family of simple. And what does simple means? Okay. So let me just drink the. This is a nice lecture because my coffee is always cold. After 2 hours of talking, I didn't notice. Okay, so simple means I didn't know that. I was, oh, simple, good, simple, semi, implicit, semi-implicit method. I write it down because it's a kind of standard in CFD. Semi-implicit method for pressure. Oh, in the name of the method, the pressure is linked equations. So basically, this means it's a name of numerical method to solve full Navier-Stokes equations in systems in which we have all the parts of the Navier-Stokes available. And now my intention now is to show you the main gradients of this simple method, because it is a kind of standard. For instance, if you know the Fluent package, so the Fluent software, which is one of the most known industrial software for solutions of fluid flow problems, it is using simple in the variant C, minus C. This is a kind of just extension for time-dependent flows, because simple in the very basic form is a solution to time-independent problems. This is a time-independent problem, the driven cavity up to some Reynolds number. The solution does not change. There are some vortices and everything, but the solution is steady. So for this, the simple method was created, and then the simple C is the way the Fluent is working. And here, for this particular problem and report, I was asked to do it by 3 methods: simple, simpler, and vorticity stream. And actually, the last one, vorticity stream, is the one that should be the easiest for you to implement during the course like this. And but all of them are available. And now let's see the first pages of the report, and then we will finish, because I want to start next week doing that. Okay, and let's see what is the main ingredient, and you will be amazed how actually maybe not simple, but straightforward it is, because it's basically the solution is based on our observation how those equations are working. Because the problem with in CFD is that we cannot solve Navier-Stokes directly. We have to do some kind of predictor-corrector steps, because these are 2 equations that work together, and the continuity equation is not fulfilled when we solve directly the momentum equation. Okay, if we solve the first equation directly, then the continuity will be basically not fulfilled. Okay, so let's see the math background again and again, the Navier-Stokes and the continuity equation. and we write them down, and that could be interesting to the person who asked about the definition of Navier-Stokes and all the terms, because now I just rewritten them. So this equation, which was on the top, I have rewritten in a form where the operators are just partial differential operators. So basically you have du over dt, that just those two equations are for the x and y component of velocity. So this one equation is basically written as two equations with partial differential operators. So basically this term, yeah, it's this one, yeah, this. Now yeah, this is the pressure, and then we have the viscosity, which is there. And the same for the y component, okay? So this you can do by yourself by taking the definition of the nabla operator, yeah, which is basically the vector of du, dy, and dz. Okay, but this is for 2 dimensions, okay? And yeah, this time I didn't know to put the left and right. Okay, and then we have an algorithm, which we will describe next week. Thank you very much. That's it. Simple method we start next week. And then, stop, I just tell you what is the follow-up. Then, after simple method, I will give you a little bit of an overview, what we do with CFD in our group, so that I want to also show you from the top approach, where did I end up with all this. And then the next 2 lectures will be about the main thing, because we will be talking about the lattice Boltzmann method and then about the OpenFOAM software. And then at the end, I will introduce you to the problems to be solved. And you, after this course, you will basically solve the problem of driven cavity with 2 methods independent. That's the idea. One written by yourself as a code, very simple. You will get a paper from myself where the fluid solver is given, and you basically rewrite it and just analyze what the code is doing. The other one you will do with a software which is open source. So this is a software that you install and you basically do it. And then your task will be to combine them together and compare and just do a little report. Yeah, and that's it. So that's the main. Thank you very much. The cards, you can leave it here. There were many questions during the lecture, but if anyone is interested, then just come and ask questions. I'm open. Yeah. Dziękuję.